Hi, everyone. In this video, we're going to go through the predicting products and identifying types of reactions. So these are the 6 reactions we're going to talk about: synthesis, decomposition, single replacement, double replacement, combustion, and acid-base neutralization. First reaction is synthesis, when we have 2 reactants forming one product. The most common examples of this are going to be like metals burning. So, for example, when you did the magnesium oxide lab, you burned magnesium, it reacted with oxygen, forming magnesium oxide. So magnesium plus oxygen yields magnesium oxide. There are some other examples you'll see as well. So let's go through some of these, starting with aluminum burns in air. So aluminum is just going to be Al, and since that's a lone element, we need to include a state symbol. That's going to be solid. If you're not sure, what's solid, what's liquid, what's gas, remember that on the walls of your classroom, the periodic table is color-coded in its letters, where black is solid, blue is liquid, and red is gas. Burns in air means plus O2, and oxygen is a gas. So these are going to come together to form aluminum oxide. Now, what you don't want to do is just smush the letters together and say AlO2. You need to form aluminum oxide in the proper ratio, just like you learned to do several weeks ago in your naming quiz. So aluminum is Al with a 3+ charge. Oxygen is O with a 2- charge. You crisscross them, and aluminum oxide is Al2O3. Okay, we're going to balance this out now. Looks like I see 3 and 2 for the oxygen, so we'll put a 3 and a 2 there, and 4 for the aluminums here. Magnesium reacts with nitrogen. Now, you're actually familiar with this from the MGO lab. This is one of the problems that you would have seen if you burned it too quickly. Instead of reacting with oxygen, which is what we wanted, it could have reacted with nitrogen as well. So here we have magnesium. That's going to be Mg solid. Reacts with nitrogen. Nitrogen is N2. Don't forget your diatomics, or what I call the Brinkelhoffs. N is one of them. So when I have nitrogen by itself, it pairs up. It's going to be a gas. So these are going to come together to form magnesium nitride. And when you work out the formula for that, Mg2+, N3-, crisscross the 3 and the 2, gives us Mg3N2. And it looks like to balance, we just need a 3 there. All right. And if you're watching this from Honors Chem, odds are there are going to be some specific cases you'll need to memorize, some unique synthesis reactions. For Chem 1-2, though, we just expect you to be able to take 2 lone elements and put them together into a compound that's the right proportion. Decomposition, you can think of this as the opposite of synthesis. Instead of 2 things becoming 1, we have 1 thing becoming 2, 1 reactant forming 2 products. For example, potassium oxide breaks down over time. So potassium oxide, it's going to be K+, O2-, so that's going to be K2O. Breaks down over time, there's your arrow. And in a decomposition reaction, we're just going to break apart into our 2 elements. So potassium and oxygen. For metals like potassium, we just write K, and potassium is a metal that's going to be a solid. For oxygen, don't forget, it's one of the diatomics, it's one of your Brinkelhoffs, so plus O2, and that's going to be a gas. We balance this out. Looks like we need a 2 there for the oxygens and a 4 there for the potassiums. Here's another example. Sodium fluoride decomposes into its elements. So sodium fluoride is going to be Na+, F-, giving us NaF. Decomposes into, that's our arrow. Its elements are sodium and fluorine. Fluorine is a diatomic, don't forget F2, and we'll need state symbols on both of these. So I just, have these memorized from doing these enough, but you could check the wall for the periodic table. Sodium would be written in black, solid. Fluorine would be written in red, gas. And it looks like we balance that with 2 there and a 2 there. Okay. There are some notable decomposition reactions that we want Chem 1-2s to know. One of them is the decomposition of water using electrolysis. This should be nothing new to you. You take water, liquid water, and using electrolysis, sometimes the method you use is written on top. So you might see like elec written on top. That's going to form its 2 elements, hydrogen and oxygen. Both of these are diatomics. So we're going to say H2 gas plus O2 gas. And we put a 2 here, 2 there, and we'll leave that one. The other one you should know is similar. Instead of water, it's hydrogen peroxide, which is H2O2. So if we have like liquid hydrogen peroxide, that's in the brown bottle, that will naturally decompose into, and this is one you should just memorize, liquid water and oxygen gas, O2 gas. Now you might wonder why these are sold in brown bottles. It's because light speeds up this process. If they sold it in a clear bottle, this process, your hydrogen peroxide would break down a lot faster. Now it's not, the brown bottle doesn't stop the process, it just slows it down a little bit. And that's why your hydrogen peroxide does have an expiration date on it. Let's see, we need to balance this. Looks like I have 3 O's over here and 2 O's. So let me put a 2 there. That gives me, looks like I just need a 2 there. Yeah, that seems balanced now. 2, 2, 1. I will just add, if you're watching from honors chemistry, again, there are probably special decomp reactions that you'll have to memorize, such as metal chlorates decompose into metal chlorides plus oxygen gas. So check with your teacher for what you need to know. Chem 1-2s, we just expect you to be able to break down a compound into its 2 elements, and you should remember these 2. And really, this top one is the same thing as a compound breaking down into its 2 elements. The bottom one's the only one that's a little different. Third type of reaction is called single replacement. This is when you have a lone element reacting with a compound, and the lone element is going to try to replace one of the elements in that compound. In general, there are 3 types of single replacements you'll see. Metals replacing metals, or at least trying to replace metals. Halogens replacing halogens. Remember, halogens are the group 17 elements, FCl-Bri. And metals replacing hydrogen. This would be if you dropped a metal into an acid. Acids are compounds with hydrogen as the cation. So the metal will try to replace the hydrogen and react with the acid. Let's do some examples. Oh, before that, using the activity series for single replacement reactions. So you'll be given one of these activity series sheets. You'll be able to use it for tests and quizzes, nothing to memorize here. And this is like the strength order of the metals and the strength order of the halogens. By strength, I mean, what has the ability to actually replace something? Elements can only replace, or the way I phrase it to my students is like to bump out elements below them on the activity series. So before you write out the products, check whether the lone element can actually replace the element it's trying to replace. So if you have an activity series sheet, take a look at it now. You'll notice like lithium is at the very top. Lithium is at the very top. And I know this is broken down into like this category, this category, this category, this category. We're not going to worry about those separate categories. That's really just like a qualitative description. So just pretend that there's no separate categories. We're going to treat it as one long list from lithium down through gold, Au. And then it's a separate list for the halogens from fluorine through iodine. You should never compare a halogen to a metal in a single replacement. You're only comparing metals to other metals, or hydrogen, and halogens to other halogens. So lithium can replace anything. Gold can replace nothing. So for example, if you have magnesium trying to replace zinc, can it do so? Yes, it can, because magnesium is above zinc. Well, what if we flip that? What if zinc tries to replace magnesium? Well, now it cannot because it's below it, and you would write no reaction or no Rx for short. All right, let's start with this one. So we have zinc added to a solution of nickel 3 nitrate. So zinc is Zn, and that's going to be solid, added to solution of nickel 3 nitrate. Remember that 3 means the nickel has a charge of 3+. Nitrate is NO3 with a charge of 1-. So this becomes Ni parentheses NO3, 3. And since I say a solution of aqueous. So what's trying to replace what here? The lone element is always going to try to replace something in the compound. I refer to this as the bully at the school dance. Shows up alone, sees nickel and nitrate happily dancing, and wants to get in there and break them up and replace one of them. So what is the zinc, which is the lone element or the bully? What's the zinc trying to replace? Well, remember, metals replace metals, halogens replace halogens, or metals replace hydrogen. Well, in this case, zinc is a metal, so it's going to try to replace nickel. which makes sense, right? Zinc's going to want to bond with nitrate because positive, negative. Zinc's not going to want to bond with nickel and replace nitrate. It doesn't make any sense. So can zinc replace Ni nickel? Well, here's zinc, here's nickel. Zinc is above nickel, so yes, this will take place. The zinc will replace it and bond with the nitrate. Now, what you don't want to do is blindly write ZnNO33. You need to think about it and write it in the right proportions. So zinc has a charge of 2+, nitrate has a charge of 1-. So zinc nitrate is going to be Zn parentheses NO3 2. Now, whenever this reaction occurs in solution like this, see how we're adding zinc to a solution of nickel 3 nitrate? This is going to end up being aqueous. And so what happens to the Ni? Well, the Ni got replaced. It got bumped out. So now we just write plus Ni. And Ni being a metal, that's going to be solid. So there's our reaction. Now we just need to balance this. Looks like for nitrates, I see 3 and 2. So I'm going to put a 2 and a 3. And then I need 3 zincs here and 2 nickels here. Aluminum is added to a sodium phosphate solution. Aluminum is Al solid, is added to sodium phosphate. Sodium is Na+, phosphate is PO4 3-. So Na3PO4, aqueous. Note that we do not put parentheses around the phosphate because there's only one of them. All right, so what's going to try to replace what here? Well, the lone element is aluminum. That's a metal. Metals replace metals. So the aluminum is going to try to replace sodium. Can it do so? No, it cannot. Aluminum is below sodium. So try as it might, it's not able to do that. So we simply write no reaction. We don't need to even finish it out or balance it. We can move on to the next problem. Hydrochloric acid, aqueous hydrogen chloride, is poured onto a piece of calcium. So aqueous hydrogen chloride would be HCl aqueous. Hydrogen is going to act as a 1+ whenever it's a cation. Is poured onto a piece of calcium. So there's Ca, that's going to be solid. All right, so what's going to try to replace what here? Well, the lone element is calcium. Remember, metals replace metals. But notice there's no metal here. Think all the way back to our starting slide. Metals can also replace hydrogen. And in fact, when you check your activity series, you'll see all of the metals here, and hydrogen is smack dab in the middle of them. So the metal will try to replace the hydrogen. Can calcium replace hydrogen? Yes, it can. So we're going to end up with calcium chloride. That's going to be CaCl2. Because this occurs in solution, aqueous, that's going to be aqueous as well. And what happens to my H? Well, the H got bumped out. Now, because H is a diatomic element of Brinkelhoff, we're going to say plus H2, and H2 is gas. So this would actually cause a fizzy reaction because you'd be producing hydrogen gas bubbles in that solution. We just need to balance this. Looks like we just need a 2 there, and we're all set. Bromine is poured into an aluminum iodide solution. Bromine is Br2, that's a diatomic. If you were to check the color, that would be blue letters, which is liquid. And I kind of hinted at that saying it's poured. Bromine is poured into an aluminum iodide solution. So Al(I3) aqueous. Okay, what's the lone element? It's bromine. Now you might say, no, that's not a lone, there's 2 of them. Well, it still counts as a lone because it's not bonded. So bromine is a halogen, it's not a metal. And remember, halogens replace halogens. So for this one, the bromine is going to try to replace the iodine, which makes sense, right? Because bromine forms a negative charge. So it's not going to want to bond with iodine, which also forms a negative. It's going to want to bond with aluminum. So for this, you're going to check just the halogens down here, FClBrI. Can Br replace I? The answer is yes, it can. So this will occur. We're going to form aluminum bromide, which is not going to be AlBr2. You got to think about it. Aluminum is 3+, bromine is 1-. So aluminum bromide is going to be AlBr3. Because this occurs in solution, this is going to be aqueous. What happens to my iodine? Well, the iodine gets bumped out. So we're going to write just plus iodine. But here's the thing. We're not going to write I3 just because there were 3 of them before. We're going to think about it. Is iodine one of the diatomics? Yes, it is. So we write I2. And if you check the wall of your classroom, you would see that iodine has black letters, which means it's a solid. We tend to think of the halogens as gases. The top 2 are, but actually bromine's a liquid and iodine's actually a solid. Balance this out with some 3s and 2s, and we're all set. The next type of reaction is called double replacement. Let me hide some of this here. So we have 2 compounds swapping ions. So think of it as like AB plus CD. So ion, cation, anion plus cation, anion. And they're just going to swap partners. In order for a double replacement to occur, we need to actually form something on the product side. When I say form something, I mean form a solid, liquid, or a gas. You're going to use a solubility table, which is generally going to be on the back of your activity series, to check the states of the products. If both products are aqueous, then nothing has formed. Now you might say, what do you mean nothing has formed? You formed an aqueous product. Well, aqueous means dissolved in water, and when an ionic compound is aqueous, it means the ions are split apart and randomly floating around. So you didn't actually form anything. So if you see aqueous as your 2 products, nothing is actually formed, and you can write no reaction, and you don't need to balance. You don't need to even finish it out. You will sometimes be able to, you'll sometimes be asked to sketch double replacement reactions, so you should know how to do that. Your teacher might sketch them slightly differently than I do, so you can go by what your teacher uses, but we all want to show what these look like using pictures when you're asked. You don't always need to do this, only when you're asked. All right, so let's write this out, and we'll include a sketch for this one. So we have aluminum iodide. It's going to be Ali3 aqueous. And potassium sulfate, that's going to be K2SO4 aqueous. I'm going to start writing these compounds a little faster now, but remember, take your time, use your ion sheet, cross the charges, do what you need to do. All right, so we're going to mix these solutions, and let's see what we get. So what I like to do is check what the products are going to be before I actually write them out. Because if there's aqueous, it's going to be no reaction, and we won't even need to write them out unless you're told to write them out on like a test or quiz. So one product is going to be the positive side of this one bonding with the negative side of this one. So it's going to be aluminum sulfate. When we check aluminum sulfate, I see aqueous. The other product is going to be the iodine from this one, which is the negative side, reacting with the positive potassium from this one. But remember, positives always come first in compounds. So it's going to be potassium iodide. Potassium iodide aqueous. So notice both products are aqueous. That means no reaction because both are going to be aqueous. Now, I do want to sketch this one out just to show, to really drive home why it's no reaction. And, a test or quiz might tell you to do a sketch even if it's no reaction. So if we're going to do a sketch, we got to finish this out anyway, just to see what it's going to look like. All right, so the aluminum bonds with sulfate. That's going to give us Al2 parentheses SO4 3. That's me crisscrossing the 3 and the 2. And as I said before, that's aqueous because I saw it in the chart. The other product is going to be Ki aqueous. I'm not going to go ahead and balance this because, nothing really occurs. I mean, you wouldn't be at fault if you did, as long as you explicitly said no reaction. But let's sketch this. So the way I do my sketches is beaker number 1 plus beaker number 2 yields beaker number 3. And I generally do the third beaker large. The idea is you're taking 2 solutions, like 2 literal beakers, and pouring them into a third beaker. Because remember, when I have Ali3, I don't have solid aluminum iodide. If you were to Google aluminum iodide right now and go to Google Images, it's probably going to be a crystally solid, usually a crystally white solid. But that's not what we have. What we have is a beaker filled with water with aluminum ions and iodide ions randomly floating around. Now, for aluminum ions, you need to include the charge. If you don't include the charge, it's not an ion. So make sure you say Al3+. Same for iodide. You have to say I-. Now, be careful, just because iodine is a diatomic, you're not going to say I2. The diatomic only applies when it's in its elemental form, when it's not an ion by itself. So I minus. Now, you might say, don't we need to add 2 more iodides? Well, yes, to show the law of conservation of mass, you would need to add 2 more iodides to really make sure it's proportional. But as a Chem 1-2 program, we generally are fine with you just showing the types of ions present, because honestly, it's just going to clog up the thing if you fill it proportionally. Now, before we move on to the next beaker, there's one other thing we need to add, which is how it interacts with water. Because aqueous solutions are all about water. I mean, aqua is water. And the water molecules are going to align themselves not randomly, but aiming in the appropriate orientation, where the oxygen part of the water, which is the partially negative side, is going to point towards the positive ion. Again, water is polar, meaning there's a positive side and a negative side. The negative side of the oxygen, of the water, is the oxygen, so it's going to point itself toward the positive ion. I may have just said that wrong. The oxygen is the negative side, so it's going to point itself towards the positive ion. The 2 hydrogens are the positive side, so they're going to point themselves toward the negative ion. I like to say these are like little fish or little tadpoles swimming towards the positive things in their lives and away from the negative things in their lives, much like we should all be trying to do. Second, we have potassium sulfate. Keep in mind, sulfate being a polyatomic ion is going to stick together as an ion. It's not going to become S and O ions. So we're going to do K plus and SO4 2 minus. Again, don't forget the charges. If you don't put charges, they're not ions. So the little tadpoles are going to swim towards the potassium and away from the sulfate. That's the waters. Final beaker. Let's see what we have. Aluminum sulfate aqueous. So aqueous means split up into ions. So here's my aluminum. Here's my sulfate ions with waters. And the number you do, kind of depends on your teacher. I just tell my students, give me enough of them so that it's very clear which way the waters point. Potassium iodide aqueous. Here's potassium. Let me do this all in the same color. Here's potassium. Here's iodide. And here are our waters. So that's our sketch. Now, your teacher might have you add certain things. Make sure you go by what your teacher says. Sometimes you have to write that this does not abide by the law of conservation of mass. Sometimes you might include just the final beaker. But this is how I always have my students do my sketches. Note this image reinforces why no reaction occurs if we have aqueous products. Look at what we started with on the left side. We had 4 ions randomly floating around in water in 2 different beakers. What do we have on the right? 4 ions randomly floating around in water in the same beaker. Notice we didn't actually form anything. I tell my students, this is like you taking 2 different soups, pouring them into the same bowl and calling yourself a gourmet chef. No, you're not. You didn't change anything. You just have the same 4 things in a different container. No reaction has occurred. Solutions of manganese 2 nitrate and ammonium phosphate are mixed. Let's do this one, including a sketch. Manganese 2 nitrate. So, well, I guess I should write out the reactants first. So Mn parentheses NO3 2 aqueous. Ammonium phosphate is going to be parentheses NH4 3 PO4 aqueous. Note when I need parentheses and when I don't. You need them when you have more than one of the polyatomic ion. One product is going to be manganese 2 phosphate. Note that the manganese started with a charge of 2+, and it's going to stay with a charge of 2+. Checking my solubility table, manganese 2 phosphate is solid. So right off the bat, I could pretty much tell this will occur. So let's write that out. Mn with a 2+ charge, PO4 with a 3- charge. The final product is Mn3 parentheses PO4 2, solid. My other product is going to be the ammonium bonding with the nitrate. Those are both +1 -1. So it's just going to be NH4 NO3, no parentheses. And for states, You can look this up and it's going to be aqueous. You do these enough and you'll notice certain patterns, such as all ammoniums are always aqueous and all nitrates are always aqueous. So clearly this one's definitely going to be aqueous. All right, so because the reaction does occur, let's balance it out. I like to start with my product with the most ions, and here I see 5 ions, so I'm going to start here. So 3 manganeses, 3 manganeses. That gives me 6 nitrates, 6 nitrates, 6 ammoniums, 6 ammoniums. Oops, one got in there. 2 phosphates, 2 phosphates. So that's my equation. All right, let's go ahead and sketch this one. So we can go a little bit faster here. All right, so I'm going to put some water in my beakers. First beaker, I have manganese ions. What's a charge of manganese? 2+. I have nitrate ions, NO3-. We're going to show some waters pointing their oxygens towards the manganese and their hydrogens towards the nitrate. Second beaker, I have ammonium, NH4+. I have phosphate, PO43-. And we're going to show waters pointing towards the positive ion and away from the negative ion. Final beaker, manganese 2-phosphate, solid. Because it's solid, it's going to settle at the bottom. All of these compounds are going to be denser than water. So this is going to settle at the bottom as Mn3 parentheses PO42. Make sure you write it together as the compound, not split into ions, because it's not aqueous, it's solid. I like to draw the line there just to drive the point home that it literally settles out in a layer. And if you did this reaction in real life, you would see, initially you'd see like a puff of like cloudy color, but given enough time, it would settle out and you would literally see like a line at the bottom of your solid product. And if you were to Google manganese 2-phosphate right now and go to images, that's what you would see forming. The other product is ammonium nitrate. Ammonium is NH4+, nitrate is NO3-. We're going to include water molecules around these. And that's our sketch. Okay. A couple of vocab terms you should be familiar with. The solid product that forms in a double replacement, this is called a precipitate. That's a noun. That is a precipitate. You can also use precipitate as a verb, and you can say manganese 2-phosphate precipitates out of the solution. Another term you should know is spectator ions. The spectator ions are the ions that start out aqueous and end up aqueous. Notice the ammonium and the nitrate didn't actually do anything in this reaction. They started out randomly floating around in water. They ended up randomly floating around in water. So they just kind of watch a reaction take place. Kind of like how the spectators at a sporting event don't really participate. They just sit around and watch. All right. That leads us to combustion. Combustion is a reaction when a hydrocarbon fuel burns in air, meaning plus O2, to produce carbon dioxide and water. Now, these produce energy as well. That's why we do combustion reactions. But energy is usually not going to be included in this type of chemical reaction, balanced equation, I mean, because it's not matter. So the key thing to remember for this, combustion is not every time you burn something. Like if you burn metal, that's not combustion. That's synthesis. We talked about that. In order for it to be combustion, the thing you're burning has to be a hydrocarbon type fuel, meaning it's H and C. Or maybe it's H and C with O in there. But it's got to be one of those HC-based fuels in order for it to be combustion. So you've probably seen these before. We like to throw these in with balancing because you get some really fun coefficients going with these. All right, for example, hexacarbon decahydride combusts. So hexacarbon would be C6, decahydride would be H10. I didn't tell you the state of matter here, so we don't need to guess. We could just continue. Combusts means plus O2 gas, that's your burning in air, is going to form CO2 gas and H2O. Now, the H2O will usually form a gas in combustion reactions. You can go by what your teacher usually recommends here, but I like to put gases for my water in combustion reactions because usually enough heat is given off that it's going to boil any liquid water that would have formed. All right, so for balancing these, I like to say H then C, then O. I like to consider evens and odds, and when in doubt, double it. So starting with my H's, 10 and 2. So I'm thinking of putting 5 here. But before I put a 5 there, I'm going to consider evens and odds. And I'm going to recognize that by putting a 5 here, that's going to give me an odd number of O's, which I can't have, because notice on the left side, my only oxygen here is even. So I'm starting to doubt myself. And when in doubt, double it. So instead of me leaving that blank and putting a 5 here, I'm going to put a 2 here and a 10 there. So instead of 5, I go 10. So my hydrogens are good. I have 2 times 10 is 20, 10 times 2 is 20, and we're even. Carbons, I now have 12 on the left. I'll put a 12 there. By the way, you're fine putting an even number here because the O's would still be even. Wait, sorry, I may have said that wrong. You're fine putting an odd number here because you would still have an even number of O's. And now we just count our oxygens and put the number here. 12 times O2 is going to be 24. 10 times O is 10. 24 and 10 is 34. Half of that is going to be 17. By the way, a little shortcut, assuming there's no oxygens here, it's going to be this coefficient plus half of that coefficient. So 12 plus 5 is 17. All right, nonane, C9H20. By the way, you're not expecting to know these names. This is if you go to college and take organic chemistry, you'll learn all about how to name these hydrocarbons. Nonane is burned. So C9H20 plus O2 gas yields CO2 gas plus H2O gas. All right, I like to do H, then C, then O. So 20 and 2, I'm thinking 10. Is a 10 going to be okay? Yeah, that's even, so 10. Carbons, 9 and 9. And yes, a 9 is fine, even though it's odd, because the whole evens and odds, I'm only thinking oxygens. All right, 9 O2s is 18. 10 O's is 10. 18 and 10 is 28. Half of that is 14. And that also works with our shortcut because 9 plus half of this is 9 plus 5, which is 14. Note that sometimes the fuel contains oxygen as well, so just be careful. In this case, butanol, which is a form of alcohol, is going to be burned. Now, this will be combusted. So we're going to go C4H9OH plus O2 gas yields CO2 gas plus H2O gas. Now you might say, why is the H out here? Why can't it be C4H10O? Well, this gets a little more than our first year of chemistry class, but when you have types of alcohols in chemistry, they always end in OH. And it's important, like that OH is what makes an alcohol an alcohol. So it's important that the OH is written afterwards. Now, if it would help you to balance it, to merge those H's and write it as C4, actually even, C4H10O, you can do that. You would then just want to change it back at the end. Let's balance this. Now, what's different about this is I have an extra oxygen here. I'm not going to forget about that. It's just different from before. I'm going to go with my same elements that I recommend, which is H, then C, then O. So for H's, I have 10 H's on the left and 5 and 2 here. So I'm thinking 5. Now, before I would have said, well, 5's a problem because that's evens and odds. But with the extra oxygen here, a 5 might work out. So let's try it. Let's put a 5. If we end up having to double it afterwards, no big deal. Carbons, 4, 4. All right, let's count our oxygens. 4 times 2 is 8. 5 times 1 is 5. So I have 13 oxygens here. So I need 13 oxygens here. Now, I could stick numbers in front of this to get more oxygens, but I don't want to do that because that would mess up my C's and H's. So why don't I leave this as a 1, meaning I need 12 more oxygens, right? Because I need 13 total. If I leave this as a 1, I need 12 more. So I'm going to put a 6 there. And turns out this is balanced. Note that this no longer obeys that little shortcut thing where I do this plus half of that because the extra O kind of throws it off. All right, let's do one more combustion. This is a famous reaction in science. In cellular respiration, glucose reacts with oxygen to form carbon dioxide and water. plus energy for our bodies. I don't necessarily want to say glucose combusts, because when I think of combustion, I think of like literally lighting up a fuel and having like a fire. I mean, that's certainly not what's happening inside your body, but the same chemical process occurs. This is also, you can think of as the opposite of photosynthesis. So we're going to have glucose, C6H12O6, reacts with oxygen. That's going to be oxygen gas to form CO2 plus H2O. Let's assume these are both gases. And in this case, maybe that, I guess, yeah, you would probably be breathing out the water vapor. Anyway, H, then C, then O. So for H, I see 12 here. I'm going to put a 6 there. For C, 6 here, 6 there. And for oxygens, let's count how many we need on the right side. 6 O2s is 12. 6 O's is 6. 12 and 6 is 18. So I need 18. Now I have 6 of them right here, and I want to leave this alone, because if I put a 2 here to get me more, that's going to mess everything else up. So let's leave that as 1. So I have 6 here, which means how many more do I need? 12 more. So I can put a 6 there, and we're good. And a little joke I say sometimes is glucose is the devil, because you end up getting 666 when you balance that one out. All right. Last type of before that, just a little note here. Everything you've seen before when we call it combustion is technically considered complete combustion. Now, you don't need to say that every time, but there's another form of combustion called incomplete combustion. You're likely not going to see reactions of this where you need to balance them, but you should be familiar enough with the concept. Like there might be a U-Texas question on this. Incomplete combustion is when combustion occurs in an area without sufficient oxygen. Sometimes incomplete combustion will occur. This would be like if you're trying to light a propane stove, like inside your tent if you're camping. Don't do that. Or if you're trying to grill hot dogs in your garage, don't do that. Or if there's a power outage and you have a gasoline power generator running in your garage, don't do that. These are all things that could be potentially fatal, because when you combust in an area without sufficient ventilation, you'll sometimes get incomplete combustion. Why is this dangerous? Because CO will form instead of CO2. CO is carbon monoxide. You, of course, know that as a silent killer, and that's the deadly part. The other product would be sometimes carbon is left over as unreacted carbon, which we refer to as soot. But so in the reaction, you actually see like plus C solid. Unless you're told otherwise, assume that all combustion is complete. So again, this is just something to know about. I wouldn't expect to be given like quiz questions on this where you have to write them out, but it's just something to know. Last type of reaction is acid-base neutralization. When you have an acid and a base reacting to form water and a salt. Now, salt, you might be thinking, oh, that means NaCl. Well, in chemistry, salt means any ionic compound. Technically, any ionic compound that's not an acid or a base. So there's thousands of possible salts. Pretty much grab any positive ion, any negative ion, put them together. As long as it's not an acid or a base, you have salt. In fact, I'm recording this on a snowy day, and I just put down rock salt on my sidewalk, and that was calcium chloride rock salt. So, you know, calcium chloride is an example of salt. Salt is not just NaCl. So how do you tell what these are? Like, how can you look at something and tell it's this? Well, acids are solutions with hydrogen as a cation. So HCl aqueous, H2SO4 aqueous, H3PO4 aqueous. These are all going to be acids. So look for H on the front of it. For bases, look for hydroxide on the back end of it. Hydroxide is OH with a charge of minus. So if you see NaOH aqueous, base. If you see SrOH2 aqueous, base. You'll later learn that there are other ways things can be bases without hydroxides, but in a true acid-base neutralization, you're looking at an acid with hydrogen in the front, bonding with a base with hydroxide in the back. And this explains why you form water, right? Because the hydrogen plus the hydroxide, H plus OH, that's your water. And then whatever the other side of the acid was, and whatever the other side of the base was, that's your salt. These reactions are really just a type of double replacement. And in fact, your chemistry teacher might not teach this as a sixth reaction. They might just categorize this under double replacements and really say there's 5 types of reactions. But I like to put this as its own reaction type, but know that it's really just a type of double replacement. Lastly, these can be tough to balance. The reason they can be tough to balance is because I love keeping polyatomic ions together. Like if I have phosphate on the left, phosphate on the right, I'm going to treat that as phosphate as opposed to P's and O's. Well, in this case, you're going to have hydroxide on one side, but you're not going to have hydroxide on the other, which would force you to break up the hydroxide into H's and O's. And it's possible to balance. It just can take a long time. So one trick you can use is to temporarily write the water as H parentheses OH, just temporarily. I know that's not proper notation. And this allows you to balance the hydrogens and hydroxides separately. And then afterwards, just erase the HOH and write it in as H2O properly. Let's do a couple of these. All right, so this is hydrogen sulfate solution called sulfuric acid. If you're watching this from honors, you should have already done all your acid naming, so you should be able to do this. Chem 1-2, we'll get to naming acids later in the year. All right, so hydrogen sulfate solution. So hydrogen is H+, sulfate is SO4 2-. So this is going to be H2SO4 aqueous. Reacts with aluminum hydroxide solution. So aluminum is Al3+, hydroxide is OH-, so Al parentheses OH3 aqueous. Don't forget the parentheses around the hydroxides if you have more than one of them. A lot of people forget that because there's, I guess, one of each that, you know, I'll see a lot of students write like ALOH3. That is not correct. All right, so reaction. So this really is, like I said, just a double replacement. So the front of this will round with the back of this. Hydrogen, hydroxide, that's going to be your liquid water, H2O, liquid. The other compound is going to be sulfate bonding with aluminum. Switch that around, positive first. So aluminum sulfate, Al3+, SO4 2- gives us Al2 parentheses SO4 3. Now, because this is a double replacement at heart, you should check your solubility table for the products. So aluminum sulfate is going to be aqueous, if we check that. Now you might say, hold on a sec, didn't we not form a solid? So didn't this not occur? Well, we didn't form a solid. We didn't form a precipitate, but we did form something. We formed liquid water, right? Liquid is not the same as aqueous. We formed liquid water, so yes, this does occur. Let's balance this out. So here's what I mean by these can be tough to balance. I see sulfate here and sulfate there, fine. I see aluminum here, fine. I see hydroxide here and, oh, we don't see hydroxide, which means I need to treat this as H's and O's separately, which means I also have to break up the sulfates into their oxygen separately, and it can just be really tricky. It's doable, it'll take a while. So what I like to do is temporarily write this as HOH. And that now allows me to keep my hydroxide separate. So let's start. I like to grab the biggest one first. That would be this one, which has the most ions. Let's start here. So 2 aluminums, 1 aluminum. So I'll stick a 2 there. That gives me how many hydroxides? 6. How many hydroxides here? 1. So I'm going to put a 6 there. That gives me 6 of these front hydrogens. Over here, I have 2 front hydrogens, so I'm going to put a 3 there. And that gives me 3 sulfates, 3 sulfates. So that's how we balance it. 3, 2, 6, 1. Now, before I'm done, I'm going to erase this. I'm going to write it properly as liquid water. Keep the coefficient, but just fix it as liquid water H2O. All right, last one. Carbonic acid, which is hydrogen carbonate solution. So hydrogen carbonate would be H+, and then CO3 2-, so that's going to be H2CO3 aqueous. Reacts with ammonium hydroxide. So ammonium is NH4+, hydroxide is OH-, so this is just going to be NH4OH. Solution means it's aqueous. And no, I'm not going to merge the H's here. It's very important to show ammonium and hydroxide, like connected as ions, but they're still their own ions. All right, so the H from this will bond with the OH from that, giving us liquid water, H2O liquid. The ammonium here will bond with the carbonate here, giving us ammonium carbonate, which is going to be parentheses NH42CO3. You can check our list here. Ammonium carbonate is aqueous, as all ammoniums are. For balancing, let's temporarily write the water as HOH, which will help us. All right. I guess I'll start with the hydrogens. I have 2 here and 1 here, so I'm going to put a 2 there. That gives me 2 hydroxides, 2 hydroxides, 2 ammoniums, 2 ammoniums, 1 carbonate, 1 carbonate. So fairly simple to balance. And I'm just going to rewrite this as H2O, and we are good to go. And I think that's it. Okay, so good luck, everyone, with your predicting products, balancing equations, and we'll see you in the next unit, which is stoichiometry. We're bringing the math back in.